Okay, so we are looking today at an alternate way of actually determining the delta H for a chemical reaction. So one of the methods that we already looked at is with Hess's law, right? So you have a mechanism that you're able to basically manipulate to get the overall delta H for a reaction. Another way of doing it is by using something known as the standard enthalpies of formation. Okay, so first of all, the standard enthalpies of formation, we've actually already seen this. It's essentially discussing the synthesis of particular molecules. So delta HF. So formation is another way of saying synthesis. So there are a whole bunch of delta HF molar values that are found in the back of your textbook. Okay, so it's Appendix C6. Or if you downloaded that reference sheet package that I had posted, it's included in that as well. So essentially, it just tells you the energy change that is involved in the formation of different molecules. So for example, if we were to talk about methane, right? So looking at how much energy would be needed to create 1 mole of methane or 1 mole of oxygen or carbon dioxide or water. So it's important to make note that things that are naturally formed do not have a delta HF value. So for example, any of the diatomic molecules, so our Hofbrinkels, right? So for example, chlorine gas. Energy does not have to be put in to create chlorine gas because chlorine gas is naturally formed. So the delta HF value for this would actually be 0. Same thing with oxygen gas or nitrogen gas, any of the Hofbrinkels, or any naturally found structures. So this also goes for anything on the periodic table that in its normal state. So for example, silver is normally found in a solid state, right? Silver is a solid at room temperature. The delta HF for solid silver would also be 0. So meaning we don't have to put energy in to create solid silver. It simply is that already at SATP conditions, right? So the same reason why we wouldn't have a 0 value for oxygen, right? Now, if we wanted to make liquid silver, obviously energy would have to go in to create this because SATP is not giving us liquid silver. You know, we have to input energy to that particular system. So when you're looking at delta HF values, if you cannot find it in the reference sheets, typically it's because, think about if it is something that is naturally formed, right? So in its, or we call it its elemental state. So meaning how would it be found as a pure element at SATP conditions? Okay, so going back to this, so we kind of understand what delta HF is, okay, but we haven't used it yet in determining overall reaction delta H values. So first we're going to kind of review Hess's law here, and I just want to show you how you can use Hess's law or delta H of formation to create or to determine enthalpy change of a reaction. So here we have the combustion of methane gas. So obviously this is the goal. We want to know what is the molar enthalpy for the combustion of methane. CH4 combustion, right? So that's really the goal. So we're going to first use it with Hess's law. So here we have a mechanism, 3 steps in this mechanism. But I also want you to notice that these mechanisms are actually delta HF reactions. So notice reaction number 1 is showing the synthesis of methane. So the delta HF value is for methane synthesis. For the second reaction, we have carbon dioxide, and then here we have water. So it's the formation of water, the formation of carbon dioxide. Now notice we're not showing the formation of oxygen because it's already in its elemental state of oxygen gas. So the delta HF value for this would be 0. So let's take a look if we were to try to manipulate these reactions to get to this overall reaction. This is essentially Hess's law. So methane we have on the product side. We want it on the reactant side with a coefficient of 1. So we'd be multiplying our first reaction by a factor of -1. Over here, we have carbon dioxide. It is on the correct side, and it has the correct coefficient. So this is actually going to stay as is. So our factor is basically 1. Water, we are producing gaseous water on the product side. However, we need 2 moles of it. Right? We need a coefficient of 2. So if we were to apply these factors and, of course, rearrange them, and we do the same thing to the delta H, right? So we do whatever factor you do here, you do the same to your delta H, and then you add those all up, right? We can use Hess's law to determine the enthalpy change. Sorry, pardon me. So I guess we can show that, we might as well. So let's show, and I'll show these kind of being flipped around. So the first equation we did, number 1, we had flipped it by a -1. So it ended up being CH4 gas becoming carbon solid plus 2H2. Okay, I won't show the delta H value because really what we want to prove is that once we add those reactions, does it equal our overall? And then we'll know that these factors were correct, right? So for the second reaction, or reaction 3 that was listed there, we kept it the same. So we just multiplied by a factor of 1. So we'll just rewrite this out. O2 gas making carbon dioxide gas. Okay, and then our last equation we multiplied by a factor of 2. So that applies to everything here. So this would be 2H2 plus oxygen, because a half times 2 is 1, making 2H2O gas. Okay, so let's take a look to see what we can cancel. So I'll use a different color here. So carbon solid, 2H2, 2H2, and we're going to collect like terms, right? So 2 oxygens are on the same side. So our overall reaction ends up being a methane plus 2 O2s, making CO2 and 2 waters. Okay, so basically we've proven with Hess's law, our factors are correct. We get the overall delta H. And then you would do the same thing to get your delta H for the reaction. So we would do 2 times our water, 1 times our carbon dioxide, and then -1 times delta HF, and then we add those all up. So we should get a value here of, so the first one was multiplied by -1. And then here we have the negative, right? So we kept this the same, -393.5 plus. So then this guy we multiplied by 2. So this is going to be plus -483.6 kilojoules, which would then add up to a total of that should be -802.7 kilojoules total. So those are our 3 added up for the delta H. Now, the question originally asked for the molar enthalpy of formation for the combustion of methane. So this reaction, so this goes back to like representing enthalpy change. Because the coefficient in front of methane is a 1, technically this reaction is the molar enthalpy for methane. So this value here is our molar enthalpy for the combustion of methane. So it's 802.7 kilojoules per mole of methane. Now, what happens if this overall reaction was with 2 in front of this? Let's say we added this up, we had a 2 in front of methane. That means when you are answering the overall question where it says what is the molar enthalpy, you would have had to divide it by that 2 to make sure that it was representing per mole. Okay, so please make sure you go back. If any of this was, right now, this should have been review. So Hess's law, we've already looked at. And we've already looked at how to interpret a reaction and the enthalpy for that reaction. So remember, anything with a coefficient of a 1, technically that is the molar enthalpy for that particular process. All right, so now let's continue on. So what is the point of this lesson? Okay, so the point is here, we want to prove that there is essentially an alternate way for determining the enthalpy of a reaction. So that's with using the enthalpies of formation. So this part here really was review of Hess's law. So now we're going to look at, well, how can we use those molar enthalpy of formations in order to determine enthalpy change? So essentially without using Hess's law. So here is our reaction, or I should say equation. So the delta H of a reaction is equal to the sum of all the enthalpies of formation for the products multiplied by their mole value minus the sum of all of the enthalpy of formation for the reactants multiplied, of course, by their mole values. Okay, so we're going to do essentially the same thing that we had done with the combustion of methane, but we're going to use this other method. Okay, so first of all, let's recall what the reaction is, right? So we have methane, plus we had 2 oxygens reacting to make CO2 plus 2 H2Os. Okay, so what we want to do is we want to look up the delta H of formations for all of the products, taking into consideration how many moles we have for each of those. So 1 mole of CO2 and 2 moles of water. We're going to add those all up. That's going to equal this first portion here. Then we're going to look up the delta HF values for all of the reactants, again, considering their molar value. So we have 1 mole of methane and 2 moles of oxygen. And that's going to become our value here. So we're going to do this minus whatever value we get for this. Now, we probably wonder, well, where do we get those numbers? Where do we get the delta HF values? So this is where you would go to your reference sheets, Appendix C6. So you have a big long list of all the different delta HF values for different molecules. Now keep in mind, the state that you look up is important. So for example, if it's a combustion reaction, we have gaseous water. So we have to look up the water gas for the delta HF. And you'll also see listed there water that's solid, water that's a liquid. So make sure like what you write for your reaction is important because the state has to match the delta HF value because it's going to take different amounts of energy depending on what state of matter you are trying to make that molecule in. All right, so just to kind of go over this, so on Appendix C6, you would look up these values. So CH4 gaseous is negative 74.4 kilojoules per mole. Oxygen, you are not going to find on your chart because it has an enthalpy of formation of 0, right? CO2, which is a gas, is going to have negative 393.5 kilojoules per mole. And then, of course, for our water, delta HF value is going to be, for gas, negative 241.8 kilojoules per mole.